I'm going to show you three different examples of average atomic mass word problems. Each one has something a little bit different in terms of what you're being asked to do with the information, but every single one of them follows the same principle in terms of how we actually calculate average atomic mass. So from these three examples, you should be able to work out all of the types of problems that I'm going to throw at you, whether it's on a worksheet or a quiz or a test. They all follow the same basic process. There's variations in terms of specific questions I could ask you once you have the information, or different ways I can present the information so that you sort of have to solve for different things. But they all use the same equation, which is that the average atomic mass is the mass of each isotope times its percentage, and then you add those results together to find the average. So let's take a look at this first one, which says you have this element X, unidentified element, and it has two isotopes, one that is 85 and one that is 87. So the first thing you always want to look at is when the information is presented with the symbol and a little number up top. That little number up top is the mass of that isotope. So we have an isotope with a mass of 85 and a mass of 87. Now it does give us these very specific mass numbers, which we're going to use. Okay, we simplify it a lot of times just by referring to the whole rounded number, because the distinction between the round number and these decimals is so tiny that we kind of don't use them a lot of the time. But when we're doing these calculations, again, the exact number isn't what's important. It's how you apply the formula. So the first isotope, it says, isotope X85, has a mass of 84.9118 AMU, and its abundance is 72.15%. Okay, so what that means is out of every 100 atoms, roughly 72 of the atoms have this mass. There's 72% of element X is a mass of 85. The other isotope, X87, has a mass of exactly 86.9092 AMU. This is one of the only times we use AMU, by the way. So the abundance of this isotope is 27.85%. So the first thing I want to point out, and this is just one of those general sort of rules of thumb to look for when you're solving these types of problems, very often there are sort of quick checks that you can do. In this case, we have one isotope that is quite a bit more abundant, 2 to 3 times, somewhere in that range, than the other, which means that when we do these weighted averages, the final answer should be closer to the first number than the second number. Okay, so the answer, the average atomic mass, should be closer to 85 than 87. That's the first thing you look for because there's just more of them. So just like in the example of the students versus the teacher, since there are more students with the lower age, the average of all the ages put together should be much closer to the younger age than the older age because there are more people with that particular age. So when we do this out, we multiply 84.9118 times the percentage. And again, you can do this either by moving the decimal point over here, or you can multiply times 72.15 and then divide by 100 at the end. It's the same mathematically either way. And then we multiply the second isotope, 86.9092 times its percent abundance or percentage of 27.85%. I chose to move the decimal point over. So we get 61.263867 and 24.20422122. We add that together for 85.4680759. Significant figure says our answer because we have these percentages here with 4 digits, our answer should have 2 decimal places, or 4 digits rather. So we round to 85.47 is the average atomic mass. Okay, now is that closer to the lower number than the higher number? Yeah, right, because if we took this, there's a difference of roughly 2. So if we took the right in the middle, it would be 85.9. So this is a little bit closer to 84 than it is to 86.9, or 84.9 than 86.9. So that's what we expect because there's more of them, so the average should be lower. The second part of the question, up to this point, this is like a standard average atomic mass problem. You've got 2 isotopes, you've got percent abundance, you multiply, add the results together, and you get the average atomic mass. If that was all the question asked, we'd be done. That would be our final answer. This one asks a little bit more of you. It says, what element is this? Okay, 85.47. Well, if we look at the periodic table, it's sort of a good rule of thumb to assume that the mass is going to be more or less double the atomic number. So we're looking for an element that's probably somewhere in the 40 range. So if I look at, say, 40 here, that's too high, that's too high, that's too high. Hey, here's 85.47, rubidium. Rb, rubidium. Okay, so based on its atomic mass, I would identify that element as rubidium because the average atomic mass matches what's on the periodic table. There will be times where I give you problems to work out the average atomic mass that it doesn't quite match what's on the periodic table. Like, for example, if I gave you numbers and you work this out, and if I said in the problem that it was rubidium, and you did the problem out and you ended up with a mass of 84, don't assume that's wrong because it doesn't match what's on the periodic table. It's just that if that's the way it works out with the numbers I give you, that's fine. Don't worry about what's actually on the periodic table. In this case, it asks you to use the periodic table to find it, so that's why I went here. Okay, now here's a different type of problem. Again, we're going to use the same formula to solve it. It says naturally occurring chlorine has 2 isotopes, chlorine 35 and chlorine 37. What is the relative abundance of each isotope? So we have the mass, 35, has a mass of 34.969, and 37 has a mass of 36.966. How am I supposed to figure out the percentages? Well, again, here we would need to look at the periodic table, and we see that chlorine has an average of 35.45. How did we get that average? How did we calculate it? Well, it was calculated by taking each isotope times its percent abundance and then adding it together. So how do we figure that out? Well, if we're talking about percentage, the convenient thing is we know the percentage has to add up to 100, or in decimals it would be 1. So if I don't know the percentage, I could say, let's say 34.969 times X. X is the percent abundance of that isotope. I don't know it, so I'm going to use the variable X, plus 36.966 times 1 minus X. Okay? Since there's only 2 isotopes, those 2 isotopes have to be 100%, or 1. Again, if we're using decimals, it's 1.00. So whatever percentage we get for the first one, the second one is the difference between that and 100%, because together they have to add up to 100%. So this is asking you to do this differently, working backward from the average atomic mass. And there's going to be several problems like this. And I want to show you every single time you get a question like this, this is how you're going to solve it. The next one is similar with a slightly different twist, and I'll show you how to solve that one. So let's carry this through. We have 35.9 0.45 equals 34.969x. Right? Just multiply those. Plus, if I do 36.966 times 1, that's 36.966 minus 36.966x. Okay, because I just distributed that 36.966 to the 1 and the x. Okay, so this is what we have here. Now I'm going to combine like terms. I subtract 36.966 from both sides, and I get negative 1.516 equals, if I subtract, I take 34.969 minus 36.966x, I get negative 1.997x. So negative 1.516 equals negative 1.997x. If I divide both sides by negative 1.997, I find that 0.7591 equals x, right? Because the negatives cancel each other out. I'm going to end up with a positive answer. And if I put that into a percentage, that would be 75.91%, which means that the other isotope is whatever percentage is left. So this, we said this was x, so that's the first isotope, 75.91%. Okay, 75%, almost 76% of chlorine atoms are that first isotope. The second one is what we get when we subtract that from 100%, which is 24.09%. Okay, so I found the percentage of 1. Once you know the percentage of 1, if there's only one other isotope, the other one has to be whatever percentage is left out of 100. So we did 100 minus 75.91, and we get 24.09. That's how you would solve this problem. Again, it's the same formula. Mass times percent abundance plus mass times percent abundance equals average. It's just this case, we had the average. We had to work backward to find the percentages. Okay, last one here. This is very similar to the one we just did, with one exception. It has 3 isotopes, magnesium 24, 25, and 26. Now that makes it a little harder, since when there's 3, any 2 of them could add up to something, and the third one would be the difference between that and 100. The trick here is they gave us one of the percentages, which means we know 1, so we take that out of 100. Then we take another one out of whatever's left, and then the last one is what's left over. So we've got 1 out of the 3, and we know the other 2 have to add up to, in this case, 90%. Because we know 1 is 10%, the other 2 have to add up to 90%. So it's slightly different from the last problem, but the same basic idea. We have to go back and find the average atomic mass of magnesium, and I'll just tell you it is 24.31. You would find that, you can just jump back real quick. It's on the periodic table here, okay, and then we're going to go back to the problem. Okay, so we've got 3 isotopes. We've got magnesium 24, which has an actual mass of 23.985. We've got number 25, which has a mass of 24. I'm having trouble with my 4s today, 0.986. And 26 has a mass of 25.983. So let's plug in the numbers. We have 24.31 equals the first isotope, 23.985, times its percent abundance. And I don't know what it is, so I'm going to call it X. Plus the second mass, which is 24.986. I do know the abundance of this, which is 10% or 0.1. Okay, that one they gave me. Plus the third isotope, which is 25.985. 0.983 times its percentage. This is where it's different. I know 10%, so the rest has to add up to 90%. So instead of saying 1 minus x, I say 0.9 minus x, okay, because that's 90%. So from here, it's just like what we did in the last problem. And again, the formula we're using here is the same as every one of these problems we'll use. Average atomic mass equals the mass of each isotope times its percent abundance, and then all added together. So let's walk through this here. So 24.31 equals 23.985x plus 2.4986. That's what I get when I multiply these two numbers together, plus 23.3847. That's what I get when I multiply 25.983 times 0.9 minus 25.983x. Combine all my like terms. I'm going to put this in two steps here so you can see where some of these are going. If I combine my x's, it's 23.985x minus 25.983x, and then I'm going to add these two numbers together. So what I end up with here is negative 1.998x plus 25.8833. Okay, so this is the sum here. This number is what I get when I subtract these two terms here. Now I can subtract 25.833 from both sides. I'm left with negative 0.15733 equals negative 1.998x. Divide to find x, and I find that x equals 0.7874, which means, since we knew this one was 10%, put it over here, run out of room, 10%, 0.7874 means this isotope, because we said x was the first one here, is 78.74. So to find the last one, it's 0.9 minus x equals 11.26%, or 0.1126, which is 11.26%. Okay, and just if you wanted to double check my math here, if you add these two numbers together, you get exactly 0.9 or 90%. So the total of these three is 100%. Okay, so those last two were very similar. It's just that this one had a third isotope mixed in with a known percentage, and then you had to deduct that known percentage from the total that the other two had to add up to. So the same formula is used for all three of these. It's just different parts of the equation being given to you, different parts you're being asked to solve for. You always have to keep in mind that whatever the percentages are, they always have to add up to 100%, and you can use that in order to solve for unknown percentages. If you were given a problem where they gave you one of the percentages and said, what's the other isotope? Just subtract the one you know from 100, and you've got the percentage of the other one, because they always have to add up to 100%. All right, so you're going to use this information, now apply it on the worksheet that you're being given, and go from there.